Hello everybody, welcome to another stream. How's it going? How are you guys? So last stream we wrapped up on the color picker. I did a tiny little bit more work off stream to finish off the little bugs, so now we can have a little button that we click on. Up comes a OK LCH color picker, so it's lightness, chroma and hue, and we can select a color. Select a color. That'll be ready for the material editor when we get started on that. But before we get started on the material editor, we need to add one more final feature. But I guess it boils down to two more final features because so that the first feature we want to add is the ability to resize the screen. Right, when you're in an editor, you want to be able to probably resize the game window. This is currently fixed size. It's hard coded to something like 900p, but maybe a little bit different to 900p. And because of that, we need to basically add a way to resize textures because we don't necessarily render straight to the swap chain. 2 seconds. Why doesn't that work? Is it because it thinks the popover's up? Right, I think it thinks the popover is up. That's probably a bug to fix. But yeah, we basically render to different textures before we render to the final screen. Okay, we've got some actual issues now. Maybe it's this thing. Oh well. Oh yeah, that widget is a popover. I remember. Yeah, so it doesn't close. So hey there, Voodoo. Welcome. How's it going? Yeah, I saw your post in the channel. I didn't realize that was your username in the Discord. Now I know. Amazing, awesome. Yeah, I saw that one in the Discord. Thank you. I'll look into that when we get started on it. Sweet, amazing. Now I've put 2 and 2 together. But yeah, welcome guys. Welcome Akraz. Welcome Video. Hope you guys are doing good. How's it going? So yeah, the screen resizing is going to basically be vital for doing an editor, right? We want screen resizing, so we need texture resizing. So currently we create different render targets at the hard-coded size of the window, and we do that when we start up the game. What we need to be able to do is be able to do it whilst the game is running. So you might be thinking, well, all you need to do is make a new one, allocate a new one, then use that, right? But there's also other ways of doing it, and like there's a whole sort of system you can build, which is what we're going to build today, where you can where basically some resources, they don't actually need to be alive for the whole duration it takes to render a frame. You might create a texture where you only render it to at the start of a frame, and read from it at the start of the frame, and then it's never used after that. So you can basically you can throw that texture away and make another one which uses kind of the same memory, maybe all of the same memory or partially the same memory. And so this is just super powerful because it allows us to, 1, create resources every frame, and 2, alias memory and therefore not using as much VRAM. So yeah, we're going to bite the bullet and make this system, and then that should help us do the resizing in a future stream. Because for resizing, we need to resize the swap chain, and we also need to resize the textures. So yeah, I guess if you want to have a bit of a what is the closest thing to this in CPU land, imagine we are probably going to build some kind of bump allocator, like a linear allocator, where we bump allocate the memory for the textures. Maybe I can draw this. So imagine every time you want to create a texture at the beginning of a frame, you check to see if you have any memory, and we don't, so then we allocate a block of memory, and then we sub-allocate from it this is GPU memory, and this is going for that texture. Then we need another texture for that frame. So we bump allocate, and we've got another region of memory for that texture. Then what happens is you realize this texture is no longer needed, so we can free it back to the system. So we need some kind of like linked list. So it is kind of like a heap allocator in a way, where we'll have two free blocks now. We have this one and this one. They are both free blocks. So essentially you will probably not bump allocate. You will probably actually have a free list, and the first free list will just be that big old entry. But yeah, so if you were to say this is used, let's say this one's used, and you're trying to allocate a new texture, you can then be like, right, this one is the best candidate, so we're going to put our other texture here, and this is deallocated. So we're going to be building this sort of system where we can essentially heap allocate from these arenas. And if you completely fill up the arena, then you bump allocate another one. So you get another arena, and you start allocating from this. And then at the beginning of the frame, all you're going to do is remove all of the allocations, and you'll keep the arenas around though. And the arenas will stay around for next frame. Then all you do is just go over the free list again, find the best fit, and use that one. It's all pretty simple stuff, allocation strategy wise. There's some things in Vulkan we've got to be aware of and that, but we'll tackle those as we get there. So we can start by just changing the interface and starting there really. I'm doing fine, still working on my uni projects. Cool. Hi there, Glorissa. Can I reuse the BVH allocator? That's a good point. That is probably what we're going to end up doing, is copy pasting the BVH allocator and making it specialized for this case. That is true. Yeah, the BVH one was specialized for allocating node elements. So this one would be allocating bytes. So it'd be like probably a general one, to be honest. But yeah, we are going to reuse that. How's it going, Glorious, sir? So these are going to probably be... So we might rename these. These are for initializing like static resources, ones that you create at the beginning of a frame. So maybe we don't allow you to ever use this later on. You know, I really don't want to add any more parameters to these functions, because there's already quite a lot. But maybe we'll have an internal one which takes in an extra parameter and does some extra bits and bobs. Right. So I might keep those for internal purposes. And then we'll probably have some kind of like lifetime enumeration. So this is probably all going to be internal stuff now, actually. So let's get this resource dnet. Not all of them. All right, let's copy paste it. So we'll probably have like initialize static static samplers. I don't think you'll have temp samplers. It maybe doesn't make sense. Right. Then we'll have another one for the temp ones. Now, when you're done with it in a frame, you probably also want to give the memory back. So we probably need to be able to say resource dealloc temp. So it's a bit different because you won't be deinitializing it. They will automatically get deinitialized at the end of the frame. So we'll build a list of them and they'll get deinitialized. Yeah, so these ones will assert if you try and use them outside of a frame begin and frame end. So outside of a command buffer, you will not be able to use these functions. And then the static ones will error if you've started any command buffers, it will error. And then the internal ones will probably use some kind of like GPU resource lifetime. So static lifetime or temporary. Good evening, how am I today? Yeah, not doing bad, thank you. I got my new phone today. Got my S23 Samsung. So I set that up briefly. I still got I was able to like set I was able to get the screen protector on and get the setup wizard to like transfer the data over automatically. So I still got to set up some of the apps. It didn't copy over all the accounts, unfortunately, for all the individual apps. But yeah, I got that, which is pretty nice. So now I have a phone which actually lasts and doesn't shut down early. And yeah, today was my last working online day of the week. Tomorrow I got the day off, and then Thursday and Friday I'll be going into the office. It'd be like a party as well, so it'd be cool. But yeah, not doing bad, thank you. How about you? How you settling in? A bit overwhelmed with uni, but fine. Nice. Yeah, I can imagine. Lots of like 5,000 word documents. Remember that. What sort of subjects are you doing at the moment? In what would you call it? Yeah, what aspects of computer science are you doing at the moment? Yes, you probably internally there'll be some lifetime passed in, and we'll store that. So this is all internal stuff. So we'll take this, and we'll go to GPU internal, get out of the public header, and we'll just drop it in here. This lifetime though, however, will go up here, and we'll simply just drop it in here. It could have honestly gone on the flags. Maybe it's better. I don't know if we'll have any other lifetime stuff. We could see if it's a flag, it'll be a bit funny. Yeah, having a dedicated enum for it is probably nicer. Let's drop in here. We can always change it if we want. Yeah, so right, that should be good. So we just got to change the internals now. So yeah, we'll start off by just changing these existing code around, and and getting the high level parts done. So all of our sort of GPU interface, and then we'll work down to the low levels and then implement that as well towards the end. So then in GPU.c, we need to take in those lifetime arguments. Yeah, I know, right? See, that was always the most interesting thing to me. I remember doing English and maths, and when I went from level 2 to level 3, so level 2 is what you do in like secondary school, or like, I'm not sure what that is in US speak. And then like when you get to the end of secondary school and go to sixth form, which is like high school, you do your A levels. So that's level 3. I remember just seeing the jump that it was for English and maths. And there was a big jump from level 2 to 3. And I never saw that jump for IT in school or in uni. It was always, you never really learned about a computer properly. It was just so weird. This is just in the UK though, where we're all like web technology, but you know, a bit weird. I think DNet static we'll call yeah, so I think we'll keep a standard DNet because you'll need that. Oh, I have an object pool and I never did it. Interesting. Oh well. And the other one was dealloc temp. We'll make sure to implement these, I think. Maybe we don't really care about the deallocate or DNet static. Cool. Rightio. We'll do that, so we'll always come back and do it. Alright, setting in pretty nice. Awesome. Got a big task on signal behavior in water and lots of stuff that I won't dare tell you about, like a program, like a microservice with this framework, please. Oh no. On signals behavior in water, interesting. Huh? Is that part of your computer science course? That's interesting. But yeah, microservices. They are the new hip. Or the current hip. Hey, Legendario. Yeah, doing good, man. I see they're using Helix nowadays. Are you happy with it? And do you have any gripes with it? Tangent is over. Helix is mostly good. I like the configuration, how simple it is. It's a configuration file. It's not a programming language. I like the fact that it comes set up out of the box very nicely. I've some gripes with the fact that a lot of things seem to be dependent on the language server protocol being like working, which is not necessarily always an easy thing for a C language. Sometimes you're just better off with just a dumb find thing, right? There's some tiny annoyances, but it comes built in with tons of like search functionality, but like Telescope from NeoVim, the plugin that TJ's made. But yeah, it's pretty cool. I like it. I don't really get to develop in it other than when I program on stream, so it's taking me a bit to get used to the new key layout. But yeah, I do like it. I think it's a nice way to start people off on a modal text editor. Although I do wish that they had simple things like pressing enter on with a line comment should carry on the line comment, but it doesn't. You know, it's little things like that. Yeah, you've zero web stuff. I'll tell you how much web stuff we had. We had web stuff where you could pass with a pass or a merit, right, which is like a C or a B, and by using a website generator known as Wix, you could pass. And as long as you could show that it had HTML, you could pass and get merit. So I got a distinction because obviously I wrote the HTML. But yeah, crazy. The thing is, you don't choose what classes you attend after you choose your specialization. You have, and they are super random all over the place. I just have to do it if I want to stay there. Uni system is super broken here. Oh no. Oh, you're in Russia, fair play. Yeah. Yeah, uni's always like 50-50 whenever you speak with someone, either they got like a real good experience or it's like terrible. Yeah. Well, hopefully you get the piece of paper which helps you get places, you know. Yeah, so these things now taking this lifetime thing, we've got these extra functions. So the basic idea is we need to make sure that we set resource lifetime to lifetime in here. And I forgot we want to have the other functions as well, right? I don't think, okay. So right, now we need to go to the header file, and we're going to bring in these new functions with slightly different names. And they're just going to call the ones below. Bear in mind, I've already got these. Get rid of that. Right, so all they're going to do is do something like this. Well, I ain't going to get much. Just end it there. Cool. Alright, so I need to go. Oh, I need to put a lifetime in there, didn't I? Right, so these are lifetime stacks. GPU resource lifetime. Let me put the rest of the parameters in. Type. Alright, so it has the downside of an extra level of indirection when debugging, but code reuse and, you know. Now we're going to also want to have an extra check where we want to make sure that if a command buffer has been started, we cannot create any more static resources. That's something that we need to do. filter and address. All right. Okay, so cool. So one more time, this time I'm doing it for temporary. GPU resource lifetime temp. Then whatever arguments go in there, and voila. So one more time. Oh shoot. Debug name, I forgot that one. No. Storage format, sample format, map levels, array layers, alias, base map, map levels, base array layer, array layers, and for the sampler filter, address mode. Cool. So dialog temp will be something more, something unique. Right. So let's actually do the core unused here. So compile. We'll come back to this. So we go to the graphics C now. We're gonna have a bunch of like texture initializers and stuff like this. These guys need to get replaced with texture init static. And then I need to put that assertion in there, don't I? I forgot about the assertions. All right. Buffer init as well. This is buffer init static. Cool. Then I think there's the texture views as well. Texture view init, texture view init static. Right, I think what I might do is remove the ability to delete. I think it might be a feature to never be allowed to deinitialize textures. And the reason being is because I don't think I need it. And this means I can, in a way, linearly allocate texture views, which would be handy. But yeah. Resource deinit. Oh, it's in the back end as well. Whoops. Interesting. Nice. Cool. So let's see what happens, right? We're going to try and run. And if it works, that's really, really great. Hey, Garcia. How's it going? Welcome, welcome. Right, so clearly we've messed up a few other places as well. Inside GPU, we seem like we internally actually create things. We forgot to put the type in here. Right, next one. Unused parameter lifetime. Buffer in it. I thought I put the lifetime in there. I didn't. Resource lifetime. And then in graphics, when we set up the sampler, no, where do we set up samplers? They're internal into, right. They're internal in here. Initialize samplers, I've got some common ones. Do static. Okay. Right, so yeah, the system still works. We've still got the game running now. So the next thing we would like to do is put those assertions in to make sure that you cannot create static resources when you've ran your first command buffer. So you do like a frame start somewhere in here. So has started frame. Right, then it gets set to false. That's not one that we want. So we want another boolean to say has recorded, has finished initializing is probably not a good one. Maybe maybe we'll literally just call it allow static or disallow static disallow static resource init. We'll just call it that. It's a very specific boolean. Yeah, so as soon as you call a frame start, you cannot create any. So simply whenever we do any of these underscore static, sorry, init static things, we'll just put a nice assertion in here. Core assert that it's not, that we don't, yeah, disallow static resource initialization, and we want to say cannot create a static resource after GPU frame start has been called. You can only create temp resources from then. Then you probably want to also put this in a function something like this, and you'll simply just call it all right, there you go. Cool. So I guess we can try and run the game now, see if it still runs okay, and we're not doing that. Right, so it still runs okay. It seems we only create static resources when we boot up the game. Let me try and just create one per frame and see what happens. So let's try and do a right, I'm trying to create this cube map. render frame. We'll drop it in here. Yeah, but it might crash. Yeah. Right, we'll stick at the end of here because on the first frame, I don't want to crash the GPU hard. Maybe. Right, first frame rendered, second frame got there, and well, I'm a bit confused. Why should it display the screen? Or would it on a submit? Yeah. Maybe that's okay. So yeah, we will get the error. Right. So let's just say that's okay. So the next thing we need to do now is actually build the internal system out for the logic for temporary resources. So temporary resources are per frame. They have a lifetime of a frame at most. So they can start anywhere from when you do frame start, you can create one. And then up until submit, you you can deallocate it and then return the memory back to the heap. So I think what we actually need to do is we might be better off getting rid of the object pool, since we're not allowing. Actually, we'll keep the object pool. Yeah, because then it'll give you a different resource ID every frame for a temp resource. That'd be good. So yeah, basically at frame submit, we need to be able to go over all the temp resources and actually deallocate the ones which haven't been deallocated yet. And then actually remove them from the object pool, all of them. So what we need to do is when you do that sort of like disallow static resources or whatever, you actually need to say, well, if that is not then we're going to take a little marker of temp resources start index. So then we go object pool. Maybe that's the thing. Nah, okay, I guess not. GPU resources pool count. How many of these guys we got? Since you only would have allocated some, and this is the start index for it, then we should be able to go over all of the resources that come after this and return them back to the object pool. And if they actually exist, we can deallocate. We wouldn't need to deallocate them, just deinitialize the Vulkan objects. Maybe defer delete them. Yeah. No, well, I've not been doing Vulkan stuff. I've been doing a whole bunch of things. Like the Vulkan's been a very small aspect of it. I think the last time I properly did a Vulkan feature was over 100 episodes ago, basically. We probably added the texture viewer, but that wasn't directly Vulkan. That was the GPU layer still. Yeah, not much. Hey Akaz, how's it going? So yeah, when we do a sort of a frame submit, you do the back and submit. Then we go over all of those ggpu dot temp. Well, I ain't really got it, have I? Temp resources start index, we'll get one of those. So we'll start from there and we'll go all the way up to resources pool capacity. No, up to the current count, that's it. Alright, so next thing to do is I think you can do like an object pool. You can get an ID from an index. At least I thought I had this feature. It's not too hard to add one. Let me get in there. Oh, you can get an ID from a pointer. How do I know if it's allocated? If I did a get, it's gonna return false, isn't it? I think I need to add a function called isAllocated, and you can check with an index. Yeah. So we get the ID from the right, so when you deallocate the slot, do you set the generations? Are you up the generations, right? Right, there's the entry is allocated bit set. Why am I doing this check here? Tempting to get an idea of a pool entry that's not allocated. Why isn't that done here? Right, it seems like I've missed this line. It's very important. Right. Allocate at, deallocate. This is the iterator. Yep, it's a clear miss. Cool. That will work. To get an entry at index, whatever, which is not allocated, cool. So we need a function which is going to allow us to check that is allocated bit set basically. So we want to know like, is an index, maybe we can make a few functions for this. Bool, object pool get, object pool is allocated, index, and then I can do, in the future if I need an ID version, we can do that. Well, You don't really need the function, but alright, let's just get it in. Can worry about making it better later. So return, return object pool that simple, I think. Wait, it's a bit set. Yoink. Rightio. So this kind of needs a type safe version, because if not calling it's going to be a bit weird. Yeah, this is why the one you get an extra level of indirection. And oh well, let's just live with it. And there's extra code gen going on. Right, we'll just live with this. Alright. So back to actually getting something done here. We want to be able to know if it's allocated. Then we can just fish out the pointer. And then we can GPU resource, so passing the address to ggpu resources pool with this index, right? So if this slot is not allocated, we're just going to continue around. So the whole point of this array is to go over all of the resources which are temporary, and they start at the, so we start the game up, we allocate all the static resources, those go at the front of the object pool, then at the back of the object pool we would bump allocate temp resources. So we're just going over these temp resources here and simply we're going to destroy or destroy all the resource data. Entries, something like this. So we're going to want to essentially do a core object pool deallocate, right? GPU resource, right? One of these guys. But this isn't just it. So you're passing the, right, you need an ID, GPU resource ID, need that function here. So this one translates a pointer to an ID, it gets the right. An ID is an index and a counter to know how many times we've freed the thing back to the object pool. So this will basically get that correct ID. And then we can free the ID like so. So that's all well and good. But right, should I free these backwards? How does the free list work again? So if we freed them backwards, we could probably move the count back. Yeah, but they're always going to be allocated, I think, at this point. Maybe that should be an assertion. So inside the object pool, we would like to know when we deallocate the slot. Yes, we create this sort of free entry thing. Something interesting that we could do is move the count back. And then you don't have to do this free list thing. So it keeps pushing it on the head of the free list. So you're probably better off doing it backwards anyway. So then they'll become linear when you allocate them again. Right. We'll do it backwards. Do the reverse loop. Yeah, so we say index equals temp resources end index minus, oh no, yeah, that one. Index minus minus greater than. The way you remember is you do an arrow. But yeah. 0. And that's it. Cool, so that decrement and then the last one becomes 0. Great, so we just want to make sure that these are actually, so this should probably just be an assertion. Expected resource to be allocated. So we never actually destroy them, just return their memory back to the pool. So we also want to probably have another assertion to say expect this to be a temp resource. So resource lifetime equals GPU. Expected temp resource but got a static one. We got something else. Right. Cool. So this will then free all the resources correctly. So the reason why I've done it backwards is, imagine if you've got this array here. Now our static ones have been allocated in the object pool, they've been bump allocated like so. And then we put a massive marker here to say this is where they, oh shoot, that's meant to be GPU temp resources start index. Yep. This is the temp resources start index. Then from here, we will then, every frame, whenever we do a buffer or texture initialize, it will basically bump allocate another one on the object pool, then another one, and another one, and another one, right? Then at the end of the frame, we'll go over backwards, and we'll put this one at the head of the free list, right? And then so after that one's been freed back, we put this one, and now this one will become the head of the free list. Also a good way of drawing it. So it'll be a free list. So this is the head. There's no really good way of doing it. So yeah, this one will be the free list head. So essentially there's a pointer that we have inside the data structure, and it will first point to this one when it gets freed. Then afterwards, it will point to this one, and inside this memory, it would store the next free element, which would be this guy. And then it will happen like that again when you go backwards and deallocate this one. And then this one will point to that one. This one will store a bit of memory in there, which will point to that one. So the free list will then be contiguous. I could have dropped the, I could have moved the count back and it will bump allocate again, but we'll just do the free list that's already in the system. So this means that when we allocate our texture views, we can allocate, whenever we do a texture view initialize one after the other, we know that they'll be contiguous in memory, which will play very well into our setup that we have when we do our in shader code, where we offset from the base texture view based on the MIP level and get the right texture view that we can then get a right resource handle. Because there's a very stupid restriction on GPUs where you cannot write to a texture MIP specifically. You have to have a texture view which is specifically viewing that single MIP. Well, it starts at the MIP that you want to write to. It's dodgy. So we're doing this for that. Right, so after we've before we actually return this memory back to the pool, which just holds the resource structure, we want to call that GPU deallocate temp, right? I guess I want to just move this all up here. We first want to deallocate the memory. Wait, do we? No, we don't care about doing this at all. Yeah, we probably want to reset the allocator wherever that is. So we'll say to do reset allocator. Maybe that calls into the backend. There might be a backend function called GPU backend. Temp resource or temp memory reset. Well, there is a backend frame thing, but we'll make it a dedicated function because then it's a bit more specific. So in the backend API, which implements the Vulkan side of things, and it can do more in the future, we'll have one which will say, okay, GPU backend temp memory reset. And this can reset all the backend pools that we have back to 0. Yeah, so we'll get to that in a bit. So I wonder if there's anything outside, and then we can go into the internals. It's got to see. So we have ways to create temporary resources with those temp functions, init temp functions. So you can create buffers and resources at the beginning of a frame. There is the assertion we need though. We need to say so this has to be only if we have started a frame. So cannot create temp resources before has been called. Something like that. Okay. So this function call will simply just go here. Like that. Nice. Right, so we've got ways to create resources, and we've got ways to automatically free all the temp resources back up. So I think from a high level perspective in the GPU library, this is done. Now we'll do all the actual Vulkan internals, which where it will get a little bit, much more hands-on. So I think where we should start is we should probably start with the memory allocation stuff, because that is the meat and potatoes of it all. Whenever we do a texture initialize, it will just call into the back end. It will know it's a temporary lifetime because the lifetime gets passed in here. And where in the back end for static ones, we just do the really simple thing in the moment. We get the size of the allocation, and then we just allocate the memory with the Vulkan memory allocation function, and that's it. This has pros and cons, right? We're a very simple game, so it doesn't really matter doing this too much. But we did this per frame. It will probably be a bad idea. So this is why we're doing this new system a bit of a different way. So I did mention briefly at the beginning, but I'll go over it again just quickly. The allocation strategy is going to be a heap allocator, but whenever a heap is full, we're going to allocate a new arena and then we've got that heap. So simply, your arenas will stick around. But if the frame, for instance, fills up, so it will go over all the heaps, find the best fit, and it will allocate a slot. Then it'll do it again, and then again, and then again. When it runs out of heaps, it will simply just do one of these VK memory allocates, and then it'll make another heap that you can then allocate from, right? And then when you end the frame, that reset function that we wrote is simply just going to remove all the bookkeeping and treat them all as being freed again, right? So that's all it's going to do. And we probably also want to have a function. I didn't quite finish the temp memory deallocate. So you would be able to pass in a GPU resource and deallocate that resource's memory back to the heap before the frame has finished, which will allow us to, that's something I did miss, which will allow us to reuse the memory before the frame is up on a different texture or something. So it'd be pretty powerful, and also quite dangerous, but that's cool. So this is in the front. Oh no, wait a minute. Whoops. GPU.c. Dealloc temp. Yeah. So ultimately it calls this, right, you get the GPU resource. And you pass in the resource here, but you probably want to make sure that you've not already done the deallocation, but I guess we could do that internally. So internally, we've got to make sure that we to do assert it if this has already been deallocated. Yeah, because you don't want to be able to people to deallocate more than once, but you do want to know. Wait, okay, I think that's another function. Every time we do a resource get, we want to make sure that it's not already been deallocated. Yeah, so we need to quickly do another function for the back end, which is probably you want to say resource is allocated, or maybe probably... Well, you could have a boolean that you store in the... You know, we've got flags, right? I don't really have to do it here. Because otherwise I have to make a backend function for every backend. It's just a bit dumb. Maybe we just put a flag here and just go, you know what? Is deallocated. Is deallocated temp, right? So it's a little bit more nice. So there's a function called resource get. We can put the assertion in there because we never really do anything with a resource that's deallocated like that. Or will we? No, we should be okay. You see, I wonder how would this work with the texture viewer, thinking about it, these temp resources. There's something to think about. So maybe we can assert here. GPU resource flag. Can I use a deallocated temp resource? Something like that. Okay, so let's just quickly ponder about this resource viewer. So the resource viewer, I guess we can run the game. Let me, in the editor, just take out the color picker. So, oh shoot, what's all this? I messed something up. Oh no. Hey Captain Chica, how's it going? How you been? Right, so we've got ourselves a texture viewer. It displays all the resources in here. These are... Your brain is upbraining today? Oh. Ooh. Yeah, this is a list of resources that exist. So I guess if we're going to support temp resources, we need to also know of all of the resources that have ever existed the previous frame and show them in here, right? If they've ever been created, we need to store their name. And then, yeah, it's a bit of a bugger, isn't it? I wonder whether I should just switch to like an enum or something dumb like that, because then they'll be persistently ID'd. Yeah, we might need to rethink the way we do resources a bit. If I want them to show up in the texture viewer, because that'll be, this is a very vital, tool. And if the temporary resources don't show up in here, we're not going to see basically anything. You can see the history of stuff is, necessity. So I think if there's a good way we can get it integrated in here, but let's not focus on that today. But yeah, something to think about. Had to fix networking drivers at work. Oh wow. Most manufacturers don't support piped I/O on their network and hardware. Oh. Huh. Can you please explain what piped I/O is? Yeah, I'm not sure what is meant by piped I/O. Okay, so I guess let's have a little side rant about Vulkan. How do you allocate memory in Vulkan? Well, it is not that simple. They got these things called memory types. So basically what you need to do is you need to make a memory requirements information structure. Yeah. Oh, it's for the null image. Me copy paste and stuff. Where's the texture one? Yeah, this is it. Right, so here's the texture initialized code. You need to create a memory requirements thing, pass in the image that you've created and hasn't got any bound memory yet. You've then have this requirement structure that you then get back data for. So this gets filled in and it tells you the size, align, and the memory type bits. Size and line are very straightforward, right? How big you need to allocate, how it needs to be aligned to a single VK memory allocation, which we'll see in a bit, and the memory types. So there's at most 32 different types of memory, so each bit represents the supported memory type for this image. So when you do a VK memory allocate and get a big block of memory, you allocate it on a memory type. So you can think of a memory type as a heap and with some special rules. So a good way of seeing this is on gpuvulkan.org. So let's go to my graphics card, RX 6600. Click on this one, I guess. You go over to memory, right? So there's different memory heaps and each have memory types. So this one has all in all quite a lot of memory types. So these have different sort of rules, but they tell you if it's like device local, or they tell you if it's host visible, if it's cached, and if you it's got these different sort of like flags and things basically. So luckily we've already selected the preferred memory types, the memory type for the images and stuff. Because the Vulkan spec says as long as you use a color image and your usage flags stay the same when you create the image, it is the memory type bits always stay the same. So we pre-select this memory type. So you won't be able to get away with this on most setups. But it's only because we keep all of these the same. And yes, it's not the most optimal, but it's just what we do. We just find a memory type, which is device local, and it's undesired to find the host visible flag. So we don't want it to be host visible if possible, but if it has to be host visible, then we'll keep it. So that's our image one. So I think actually we might have one allocation system for images and another allocation system for buffers. What also makes the Vulkan allocation stuff really annoying, if you want to stick buffers and images in the same allocation, same VK allocation, there's a thing called buffer image granularity. It happens to be one on my device, which means you can put images and buffers right next to each other without any alignment issues. But some hardware will want you to put extra alignment between a buffer and an image for some reason. So sticking buffers and images in the same VK memory allocation or VK allocate memory is problematic. So it's another thing you want to be careful. So I think we can actually get away with a somewhat simple system. So I think inside GPU internal, I want to make a memory allocator or a custom allocator for so we can call this like a range allocator. And we'll copy the one from the graphics system. And we'll just rework it. You put flags on the higher bits on a single byte and continuously read write to a buffer somewhere in memory with size encoded in the low bits. Right. But what's the accomplishment of piped IO? What does that get you? So in the graphics system, we did a BVH node allocator or node range allocator. We're just going to copy this and refactor it. Now the problem is that it's not. Yeah, it's okay. I think it can work. So this used to do elements, a range of elements. This one's now going to just do a range of bytes. BVH node. All right. So it has a start. So we could say that each block. Oh, okay. How are we going to do this? Yes, there's a power of two bucket system. So the problem is the GPU one, you're going to need different heaps. So you need heaps and blocks. So a heap might contain blocks, is that fair? Right, so heap might just contain a size. So you go. So I wonder, should we? I think we've done over 4 gigs, so we'll just do that. So we'll say it's got a size. So I want to make this one a little bit more agnostic to the backends, maybe. But perhaps. Perhaps that's not a good idea. Yeah, so I guess you have a heap, it's just got a size. And a block will always reference what heap it comes from. So there's a start and end index within the heap. So if we kept this separate from the back end, it means that yeah, you know what, we might be better off sticking it in the Vulkan layer, because I don't know when I'm going to port to another platform. Let's just make it work well for the Vulkan one. It's going to add extra friction now, so let's just get it in the Vulkan layer first. It's probably a better idea. Vulkan internal. Right, so I have a GPU range allocator. GPU Vulkan range. Or a memory allocator, we'll call it that. GPU Vulkan memory heap. Mem heap. Mem block. Right. Seems good. Typo. No. No. Thank you. And I didn't go the full way anyway. Kind of got excited and stopped. GPU Vulkan. I did it again. So basically, maybe within this stream we can have our own allocator, you know, and I wouldn't even be using VMA. Isn't that great? So heap needs a VK memory handle thing, device memory, that's what it's called. So there's your device memory. I like to prefix all the Vulkan stuff with VK, just so, you know, I know what it is and everything else is not Vulkan, right? Has a size, something like that maybe. Yeah, so I have a linked list of blocks. Oh, the TikTok bit, I remember that TikTok bit. Yeah, I forgot what it was for now. So maybe it was to do with yeah, it's to do with the validation side of things. That was it. I have a function which basically tests the whole system out. And the TikTok thing was used to do that somehow. Right, I think we shortened it to VK. Past Henry knows where it's at. GPU VK range. No, mem allocator. Yeah, that's what we want. Right, another rename. Alright, we're looking good. So I think these are all pretty good. This has messed up how perfect this was, I think. No, because they are 4 bytes and then 4 bytes. That's still okay. So 4 bytes, 8 bytes. That was going to be 16 bytes, wasn't it? Wait. Yes, another 8 bytes, so 16 bytes. So I just made it 20 bytes, but that's okay. Not the end of the world. Number of nodes. So it's not really in nodes anymore. It's just we don't have an overall capacity. Validate TikTok bit. I forgot why that's there. Not gonna lie. You can always delete it and figure it out. Maybe it needs to go on the heap. Unused list block ID. Right. So we keep the blocks around. Oh, okay. Some of these are U16s. The U16s are fine for blocks. Yeah, U32s are fine for those as well. What's a block start and end index for again? Oh, so it has a continuous set of blocks. That's it, isn't it? That was for validation side of things, was it? So you knew the ones next to each other in memory. Yeah. Yeah, we didn't necessarily need that. Maybe we can stick it in the heap. So the heaps can have their sort of like block start, index. And this is a linked list of all these unused blocks which are not in the heap. And the blocks will link to each other, so with a next and previous ID. Free list power of 2, and here's the power of 2 buckets. So you'll go index using the power of 2, and then get a block ID. Then you go into the blocks, get your block, and then there'll be a free list next ID where you can go to the next one. Cool. That's all right. Yeah, that'll be good enough, I think. So let's go ahead and get the implementations. This will be the memory allocator. You know exactly when a network request is done, timed out, rejected because different flag will be set. Right, okay. Fair enough. Do you do like do you work on kernel features then, is it? Or is this something else? What is your day job? Remember you telling me before, maybe? I forgot it, if so. Right, so we need to add this memory allocator. So let's go into the graphics. We'll find the node allocator stuff. Again, we're just going to copy it. Going to steal past Henry's work and get some more reuse out of it. And just do some lovely renaming. Why is that all with a bunch of spaces? Okay. So here's the memory allocator. And so BVH node range is going to get replaced with GPU VK memory or mem. Let's quickly go over all these boys and girls. Right, I wonder if there's a bunch of internal functions that I missed. That was a lot. Node range, GPU VKMem. Currently working at how? Currently working out hardware abstraction layer maybe, and memory for kernel specialized hardware specific uses. Awesome. Sounds pretty fun. Right. So it seems like we did miss some functions. So I think if we go into graphics internal, we'll find some more. Oh, there's an internal API. It was off the screen. You bugger. Right, let's go into the header file quick. Somebody didn't scroll far enough. So there's an internal API which allows us to get blocks and stuff. Right. Right, so next job is to go over this implementation code and adjust it to have heaps and actually allocate VK device memory. We're going to also need to make sure that this has a very specific memory type index. VK memory type index. So we have one for buffers, one for textures. Yeah. Just stuff before this was piping large image data through device with 500 megahertz CPU and 64K words of memory. Wow. Bananas. That was fun. Networking was left to be written in the 10th layer of hell. Oh. Sounds pretty diabolical. Yeah, so just got to go over this system and just remember what it does. Got a quite good idea. But yeah, we need to adjust it for the whole Vulkan's madness. But we've restricted the amount of Vulkan madness that we need to do by making us have one memory allocator per memory type. And that should be good enough, basically. And we need a way to remove all the blocks at the end of a frame as well. Right, I'm just going to take a quick minute break and get a drink, and then we'll come back, go over all these functions, and do all the lovely custom allocator stuff. Right, PLB. Oh, welcome back, guys. Yeah, Dante might have been an hour, but it wasn't. It hasn't written as for networking devices. Right, so when we initialize one of these Vulkan memory allocator thingies, right, it's not a lot of nodes. Nodes is a terrible name. But yeah, I think it's just... So also capacity is kind of a bit of a terrible name. What do we want to achieve here? Well, I think we probably want to define some kind of size that we allocate, but that could probably just be a constant. So realistically, the number of blocks is something that we could probably pass in, but could also just be a constant. So effectively, we could just do something like this, or we say vk mem allocator. We want to have like a heap min capacity. So this is the minimum size that we're going to allocate. If the resource is bigger than this, we will allocate a bigger chunk of memory. So from if memory serves, a 4K square texture is a 4. Oh, it is. I didn't press that key. So 4K square texture. So at 16 bytes per pixel is 256 megs. But if you did it as a 4 byte per channel, it's 64 meg. So we could probably, something worth thinking about. Are we going to have many resources which are 4K square textures of? The answer is no. So we could probably say, you know what, 250. So if we're going to have a 4K texture, typically it's not going to be 4K squared, and it's going to be probably 4 bytes per pixel. So maybe we could get away with 128 megabyte heap sizes. So I think I got core megabytes. I think I got one of these. Yeah. So let's say 120 meg. Yeah, because it's not going to be square. It's going to typically be like 4K, kind of the widest dimension. And it'll only be 4 bytes per pixel. So you'll fit a few textures at least in a single heap. So the other one as well is the number of blocks, or the maximum number of blocks you'll have in the whole system. So you know, 4096 is quite a lot of blocks. We could probably just say, give us a block for every number of resources that you have, right? So actually, we don't need that either, right? So the most number of allocations we'll ever have is with the maximum number of resources we actually have in the system. So yeah. So when we allocate, this would be a number of bytes. So bytes. Hang on a minute, there's going to be some rules of alignment as well. So size and align. Yep. Which the other system, oh shoot, what did I do? And then you free the block back. There's also a defrag system, which we probably won't need. So we could probably delete that. Or you defrag a block at a time. Shrink to, we never have that. We can delete those. Print, all right, validate, all right. Test, all right, we'll keep that. Get a block index, yep. Get a block from a index. Block allocate, which is a separate kind of thing. It's like just give me a block from the unused pile. Deallocate a block itself. Unlink from the free list. Next free list head. Set free list head. Right, I see. Bucket index. Define bucket index for insert. Brilliant. This one uses nodes. So how many nodes? So we want to say probably just a size, because the alignment will come after. Hey Chris, how's it going? Yeah, I did finish the color picker. I'll give you a quick show. Hey Omni. Yeah man, doing well, thank you. Good to see you too. How you been? Hey Ross Compiler. I see you again. Ran into a problem where I had to create a let's create a callable method pointer. Oh my days, that sounds bananas. Also, sorry, that also needs to store parameter in, so end up writing meta parameter, take any function, turn it into a function pointer, plus a struct that contains a pointer and data params. Wow, that sounds very... But yeah, if you achieved it, that's cool, amazing. Has it solved your problem with the variable length callbacks? Yeah, so we added in the editor, so we've been starting working on the goal, the immediate, the high level goal is to build some editors now so we can build content. So we started building a color picker because that was needed for the, that is needed for the material editor. So we built a OKLCB color picker. So here's the widget, you can click on it and select a color. If you go outside, it will only keep the one that's inside the sRGB color gamut. So this allows us to select a color, which is, yeah, select a color, change the hue, and the perceptual brightness will stay the same. So it's pretty powerful stuff, but obviously not all colors are, you know, can have this perceptually the same brightness at different lightness and chroma. So this is a lightness across the X and chroma across the Y. So chroma is how saturated it is. And then we've got different graphs which swap the 3D coordinates around. So this is the lightness on the right. And then it's chroma and a hue in here. It's pretty powerful stuff. It'll be pretty cool for the material editor when it's there. Select some colors. So that's all done. Check that one off, which is sweet. So working on actually resizing the screen today. So, yeah. Something I've definitely delayed for a very long time. But yeah, also, I also built this encoder system, which is very nearly finished, but I've been working on it off stream. It's basically a code generator for serialization. So that's been going quite well. I'm just literally getting it in for testing, and it outputs a CSON file, which is a C version of JSON. Look at this beauty. It's just a bunch of random fields that I've chucked in, but it supports strings and structures. You get the type names in here, and so this is the human readable format, but it also does binary formats, versioning and things. So it's quite nice. I'm trying to read it in at the moment and get it to work. That's got some bugs. But yeah, output's just fine. Just trying to read it in. So we worked on like a little code generator for that. Yeah, swap chain recreation. Yeah, it's that will come next. I'm doing the temp resource stuff, but yeah, it's a bit fiddly as well, but it's possible. You gotta like. Also, you've got a bunch of texture resources that are the same size as the swap chain, so you're like, gotta have a way to create those as well. In a good way, right? We don't want to do something quick and easy. I was thinking, we'll just do something quick and easy. And I was just thinking about how we'll basically end up with a code base, which is just something I'm going to hate. So I'd rather just do it properly this time, and then we won't have to do it properly later on when I get to a place where I'm like, this code is just not in a good place for me to even do something with anymore, and all falls apart, and I have to actually go in and do the work properly. So just doing it properly the first time. Yeah, I use Vulkan 1.3. Yeah, it's the latest and greatest Vulkan. It's got some good features in it. Yeah, I was hoping they would do a 1.4 soon, but I'm always like hoping they're going to do something really crazy. But that's just me getting my hopes up. I looked at how Godot does method binding and decided on using a custom program to look up, and code generator is much easier to read. Fair play. Huh. What are you talking about method binding? Is that with a scripting language? Right. So when you instantiate said memory allocator, we simply just don't do that check. We zero the thing. This is equal to, so the number of blocks at most will be the capacity of the resources pool. That's pretty nice. Specialized code wins. Then we always allocate a single block when you have a heap. So you're always going to have at least one block. Now, the thing is, when you allocate a block, you have to... Oh, shoot. This is not a heap, though, is it? We don't have a heap yet. We always need at least one. Yeah, so we should always allocate the first heap. That would be a good idea. Maybe we need a memory type. A VK memory type index to come in. That would be pretty useful. The Aston Martin Vulkan. Sure. Right. Looks pretty dope. I like the bonnet looks pretty cool. Definitely seen this car. That spoiler's huge though. Imagine the weight on that. Pretty dope. My days, they ain't going over any speed bumps. Just rip the car apart. Alright, worst hypercar apparently. Clickbait. Yeah, that's pretty dope. I like the sticks. Displaying the reflection for C? No. So calling method, it's like having a call, right? Okay. I see. Right. Was watching resizing, you have a sneaky issue with OS window interactions. Yeah. Yeah, the spec doesn't specify how things are. And I remember there was that Vulkan swap chain example. Now they released this like years later. There's the correct way to do it. And it's probably all filled with C++ crap. There's like a preferred way to, or there's a correct way to do it, and it's a lot to take in. I don't want to trust any tutorial on the internet because yeah, it was a sample. That's probably what it was called. And also the crazy thing as well is they have a way to recreate the swap chain, but when you look at the VK cube source code, it actually destroys the swap chain first and then creates a new one anyway. It doesn't use the recreate API. And yeah, there's a bug I remember I had because of that. And this ain't it. But yeah, there was a specific like GitHub sample. Kronos group Vulkan samples, probably in here somewhere. Yeah, it's in here. Vulkan samples. I can feel the C++ already. API, I guess. General. API. Swap chain recreation, here it is. I'll drop the link in it if you guys are interested. I think I saw it's linked on Twitter back in the day. But yeah, they talk, they say this is the presentation engine and here's these things, and they give you like ASCII diagrams and with maintenance 1, or swap chain maintenance 1, all the above is unnecessary. Each QP. Q present, here we go, can have an associated fence, which can be used to know when the semaphore associated with it can be recycled. Yeah, you have to like do stuff with it's bananas. The old swap chain can be destroyed at the same time as before. Yeah, so I'll leave this one open for future. But yeah, this is what we'll probably look at. Get it right. Oh yeah, that's a good point. Is the extension even like something that's even supported well? Did it become core? No, it didn't become core, which means it's hopefully supported well. And this is pretty crap now because, okay, it's a good service, but I at least don't know how do I filter out all the Android devices. Because, yeah. You know, if you can go at least version 1.3 and then get stats on that, that would be good. Maybe there's a way to do it with the query language stuff, but I don't know. But yeah, it says 22%, whatever that means nowadays. I don't know. Yeah, so it's probably not, you probably can't just use this extension. So yeah, there's probably these query things you can do where you can say version, I reckon. Yeah, I reckon you can look at that PHP page source code and figure out if there's ways to make it go a particular version. I don't know. But yeah, probably can't rely on that extension. Windows drivers did not support suboptimal presenting, so that was a bit of a problem before I could render a frame. The window already resized again. Right, interesting. Huh. Yeah, I always just redid it on the suboptimal thing anyway. But yeah, maybe it was a good idea to render on suboptimal because it made this resize smooth. I don't know. Oh, Vulkan is C, but Kronos, whenever they do anything else with Vulkan, they're like, they C++ everything, usually. Well, this ain't C++ API. But yeah, they do everything else C++. It's bloody annoying. Grinds my gears. What I did was this, resize the swap chain only after the user stopped resizing the window, painting the window black with the Win API during resize. Yeah, that sounds like a sensible idea. The thing is though, is I want to know how the hell the web browser does it. Because look how good this works. And I've never been able to do this. So I guess we're gonna do, see how good that is? If I do it fast, you see it. But it's still pretty good. Whenever I've done it, it's been like so bad. Ignoring that sort of text thing, if I get like a basic website, it's pretty smooth. Whenever I've done it, this border bit has always been lagging behind, and I've never been able to be that fast. But I guess I think they're using the GPU, right? Don't know. I don't know what's going on. We're gonna try and do a good job at it. Yeah, I've probably got it as well, but you only really want to use extensions like that if it supports on all of your hardware. If not, you've got to support both branches, or both of them. So you might as well just not support those types of extensions. That is an easy way to do it if you don't want to be presenting while the user is resizing a window, yeah. Yeah, I guess other ways are you could quickly try and present as fast as possible while the screen is resizing, but I don't know how you would do that. Yeah, but I did it using OpenGL Acros and I couldn't get it that smooth. So I don't know what magic the people are doing. Maybe, yeah, so I'm going to try and achieve such thing. I've never been able to resize a window that smooth and I don't know why. But obviously, present Henry is better than all those past Henrys I tried, so maybe we'll be able to do it this time. You can do it too after a resize the swap chain, push out a frame, and wait for the present to happen before you allow more window resizing. Allow. You can stop the window system from resizing a window. Huh. I wonder how you do that. If so, that would be amazing. So you would just, on Windows you can. You must be able to do it on Linux then. If that might be the secret. Yeah, so memory type index comes in. We've got to store it in the allocator. Allocator. So we'll allocate all the blocks and all the heaps. I guess we'll just waste memory, just over allocate it. Doesn't matter. Okay, so what we will probably be better off doing is actually, so I want another internal function for this. I want to be able to allocate a new heap. So this is where the fun begins. Let's just get in there and just complete it all. Let's do the Vulkan memory allocation and everything. So we got ourselves the heap. I think you just do a yeah, you just do a core stack push on allocator heaps. You will try and figure out the size. Right, so the size would be equal to, well, I guess you just say size equals the maximum of whatever the min and whatever the current size and the required size that you need. All right. So after you create a heap, you also need to create a block. So you'll probably block allocate. So we get an unused block, and what will you do? Yeah, you'll make a new free block. So I guess you could just say you'll make a new block. You've got to set the heap index. So yeah, I guess you would just call that function gpvk mem allocator heap index, passing the allocator in the heap. Set that boy up. Maybe when you allocate a block, you always pass in a heap, and it sets that up maybe. Like, hey, this is the heap it belongs to. Sounds pretty reasonable. So this line just goes here. Then we pass in the heap like so. So after you create the block, so it's a free block, and it is whatever the heap size is, right? So it spans the whole size of the heap. Then we need to it also needs to be put onto the start and end indices correctly, something like that. Yeah, where's that done? Block. When would it ever set these up okay? What is going on? Huh. Right, skip to the graphics side of things and look at the... When did we set these up? Oh, so it's when you deallocated the block. But why never when you allocated a block did it do it? Right, I think that code broke. Whoops. But yeah, when you allocate a block... maybe we won't bother with that code. No, we'll need to do it at some point. Right, so when you have the heap, you need to allocate this VK device memory thing. So VK allocate memory. All right, this is it. So we should be careful with our asserts in the future. But if we run out of memory, it's going to assert. But yeah, that'll be a thing that future Henry will tackle. Right, so put it in the heap when it's done, and the size that we want is whatever heap size is, and the memory type is stored in the allocator when we initialize it. So I'll allocate the Vulkan memory. We'll put a block which spans the whole range, and we should probably say for the heap, GPU block index. So the start and end of the whole region. So if you just take the heap, the first block in a contiguous space is this block, and it ends with this block. That's what we're saying there. All right, so I think we filled in everything there when we do one of these sort of like heap allocate things. So in the instantiate function, we can simply after we initialize all the heap, the array of heaps and the array of blocks, or the arrays for those at least, they don't have anything, it's an empty array. You pass in the allocate, and the required size can just be 0. And voila, we should allocate a heap. The first heap, and would always have at least one block in the free list. Set free list head, right. So I think we can say GPU VK memory heap, and then we can get the block VK and the block index would be heap star index like that. We put in the block. Yeah, then we say this block is, we set the free list head. Yes, this is going to basically, if there's already a free list head block, it's going to make it point to the new head. Or make the new head point to the old head, basically, something like this. And it uses a power of 2 system for the buckets. Yes. Right, there's stuff we've got to figure out still. Let's leave that one alone. Hey Solly, how you doing? Welcome, sir. How's things? Yeah, I think we'll get down to this one. Let's just keep going. So we want to keep our, well, maybe we should fix. Yeah, let's just go in a linear order, maybe. Right, so allocate needs size and line. All right. I guess we could say let's just, put some asserts in there. And then some of that. We should really check for powers of 2 as well, but some of that. Cool. Right. So this allocator that it came from would, yeah, it did some tricks basically with the alignment. So because this is, so it used to always have 4 alignment. So that's all it needed to know. Everything got rounded up to be in 4. And so that means when we allocate stuff, everything was guaranteed to be 4 aligned. We can't have that same assumption in this allocator, so things are going to have to change, unfortunately. So it used to be a nodes thing, but now it's per byte. So it's different. To take the nodes count and find the next of 2. Well, I meant to say next power of 2. So yeah, take the size and find the next power of 2. Then search for that power of 2 bucket until we find a free block. So so the issue is we cannot simply just we cannot just look at the free list head. Oh, yeah, the alignment could be anything, which is crazy. We could always see. I wonder if there is some form of max alignment, but there will be wastage. I wonder if there's any max alignment that we can do just to keep code simple. We can check the Vulkan header. That's typically got a good source of things. Let's check the Vulkan header. So open user include Vulkan core CPPM. Oh, disgusting. So if we look for like a line, is it with allocation callbacks? No. We're doing a temporary allocation system for resources. So resources that have a frame lifetime or shorter. So we're doing a custom allocator on GPU. So you could turn on all of the bits. This would be pretty sketchy, right? Turn on every single requirement and ask for the memory type. I don't think that's guaranteed by the spec, but you would think that it would work that way. And maybe you can't turn on all the usage flags. Maybe that's a yeah, that, damn it. That would be pretty sketchy. Because honestly, anything past in null is probably a waste of time. Well, yeah, so the thing is, it's a waste of time when you start doing Vulkan. There's no point doing it. It's just, yeah, doesn't solve anything. But when you have a game that is ready to be shipped and you're optimizing, probably a good idea that you do it. You know, but right, we come full circle. There's nothing to do with alignment. Wait, have we? Yeah, nothing to do with some form of maximum alignment, which would be nice. But we could read the spec and see if we can read between the lines on things. But yeah, I think so. The spec could say. So the spec definitely says if the usage flags stay the same and it's a color format, you get the same alignment. You're guaranteed to have the same alignment. But it doesn't say anything about the alignments that guarantees be greater than if it's got more. Wait, does it? It does say that. I think I remember seeing it. Right, let's get the spec out. Oh, Vulkan spec chunked. You always have to explicitly search for the chunked version for some reason, because the chunked version just loads instantly. But yeah, but you have to actually find the page. And everything links to the non-chunked version. It's bloody annoying. But anyway, so we're looking for allocation. VK allocated memory, is that right? device memory allocation. Do we want to look at that? We're looking specifically for the memory type bits. It's probably the requirements. What page are we on? I guess this is the problem with the chunked version, is you don't get. It is probably this association one. Yeah, this is it. Right, here we go. Right, this is... Right, so we don't care about buff... Yeah, so for buffers, as long as the usage flags stay the same. Right, but this was the logic, isn't it? Further, if usage 1 and usage 2 are such bits... are such that the bits in usage 2 are a subset of usage 1, they have the same flags, then the bits set in memory type bits must be a subset of the memory. Ah, damn it. This is what I was remembering. So it's the subset of memory types. This is not what we care about. Talk about the alignment. Right, alignment is power of 2. That's for a buffer. Right, is this it? Okay, so there's no special rules for alignment and images. By the looks of it, just memory type bits. Okay. So I guess we can't do anything like fix allocate a big range of... Alright, so we've got to do it properly. So the best thing about this system was that you have power of 2 buckets, you take the size, you round it up to the nearest power of 2, and you can work out based on things which you've got to update. You can find out which bucket to look in. That bucket will give you a linked list of blocks which all have at least your size in there. So that means you'll be able to take the first block and just use it. So it's the lookup will just take you straight to an allocation which is perfect for you. The problem is we also have alignment now. So the way you typically solve this is you basically take the alignment, you add 1 minus the alignment on to the size, and that will guarantee you enough to offset in it. So you just do something like that, bit jank, but this will guarantee that will get put in a bucket where it has at least the size of size plus align minus 1. And we can then align the memory in the block to the alignment, and we will never overflow that range that we've allocated from the block. So that's effectively what we're going to do. So I think we can just do it from the get-go here and just say size plus equals align minus 1. And we can just say this is so we can this is so we can align the pad the size so we can align any block we find. Something like this. So it has enough room to align any block we find. So yeah, we do that trick, right, where we just get an index for a bucket, go over all the power 2 buckets. Usually you just get the first one. So this is our, if this power of 2 bucket has anything in it, we just use that one. If it doesn't, we go to the next size up and we use that one. So then we get the block. We say the block is not free anymore. Then we unlink the block from the free list. And see, my concern is... Oh no, okay, you'll get it from any heap. Yeah, that's true. Then you need to say... So next free list head, bucket index. Very weird function name. I'm not sure what I was thinking when I named this. So you get the bucket index. You get the block. Oh, okay, so it just cycles to the next free list head. So this is the free item, it'll just cycle to the next one. And then this gets the number of nodes. So I guess this function here that we're looking at is actually going to be called block size. So I get the size of the block, and we can just assert to make sure there's enough room. And then if it's exactly, if you know the shoe fits exactly, we just return the block. If it doesn't, the shrink. I guess we need that shrink to function, or we shall revive that. So a shrink will basically make the tail end of the block be a new free block that gets added to the free list. So we need to sort out this function here. This should be no longer really a I don't know what's going on here. Vulkan internal. Did I delete those guys? I think I just didn't have them in the header file, which is weird. Huh. Right, I think I just deleted it. But yeah, this will just, we just want to say what is the block size. So it's just that ready. We'll make it U64. I think we want to be careful with some of these integers as well. All right. Cool. So back to the allocate function. Yeah, so this will get the block size. Size of the block. Nice. If it's a perfect fit, we'll just return the block. If not, we'll do the shrink. So this shrink, I don't know if it gets used anywhere, but I had it as a separate function because it was something I wanted as as functionality, but we don't need that anymore. So we're just going to take this and put it here. So all this nodes count stuff, we just swap out for size. All right. Yeah, so you get the block ID for this block. You get the old size. These should be returning U64s. Which means they also probably need a ZU in there. See the old size for the block. Do you always return block? Yeah. So if it's a perfect fit, which we've already checked above, right, so let's look for old size. Right, it's no longer needed. Cool. Okay, so you make a free block, which means you need the heap. That'll just be GPVK heap. I do not have one of those guys. Yeah, we need a heap get. U16 heap index. Then we add some thing. Oh no, it's just one of these. Just do a core stack get, which already does the checking for out of bounds and stuff. Right. So back to here, we want to pass in the allocator. Then in the block, it also has that. We have the heap index in there. Yeah. So that was stored as a U32. We could probably get away with U16, but then it's going to have extra padding. So yeah, we're using U64s for sizes though, which mean blocks probably also need to have 64 for start and end, I reckon. Yep, okay. So we get the heap, then we get the pass in the heap whenever we allocate a new block. So this is that free block which starts after the block we've just allocated. So we take block, add the size, and it points to the same end. It will then start after the previous block in memory will point to would be the block that we've just allocated, and we return it to the user, and wherever it was next pointing to free list. Yeah, it gets set later, basically gets put in the free list, and it is a free block. So then we do this set free list head on this new free block we just made, and that'll set this up and make it the new free list head. Then we get the free block ID, and if we have a next block ID, we make it point back to the new free block ID. And then, so this is for all the stuff that sits contiguous in memory, all the blocks that sit contiguous in memory, they will link to each other. Well, the memory they reference is contiguous, they will link to each other. And if it doesn't have one, then in the allocator, which is wrong now, in the heap, it's going to set the end index to be this free block index. And then we finally update the block that we've allocated and returned to the user. And we say the byte end position is equal to the free block start position. And the next ID is the free block ID. Didn't we already do that? No, we didn't. Right, yeah. Okay, so that's one down, another to go. So deallocate, it gets the block ID, right? If it's not a free block, sorry, if it is a free block, it's going to complain that we've freed more than once. We check to see if there is a free previous or next block. If we've got a block that came before us and is after us, we basically just join those guys together. That seems to be pretty sensible to me. And then if there's a previous one, we will join it with the previous one. And if there's only a next free one, we'll join it with the next free one. And this deals with like putting it in the free list and stuff like this. Sorry, unlinking stuff from the free list and stuff like that. So when you deallocate this one, block deallocate, it unlinks it from the free list if it was a free block, stuff like that. Right, and then add a block to the head of the free list. Sorry. Add block to the head of the free list and make old head point back to the next head. So I guess we're always... Right, I see. So we always deallocate the other neighboring free block, and then we'll put ourselves back in the free list. Nice. That makes sense. Since you're merging, right, the block becomes bigger, therefore it goes into a different bucket typically. Cool. Defrag we do not need, since we're going to defrag at the beginning of the frame when we delete everything. So we'll need a function which deletes everything. So I guess we could make that instead. So rather than defrag, I think what we want is a reset. I just deleted the defrag. Ain't I good? So yes, it's just a reset. It's just going to completely... So what it needs to do is get it back to the original state. Just get it completely back to that original state. So what we could do is we could clear the... Let's look at the allocator. We can clear the heap and the blocks. Just clear those arrays and set this unused block ID back to 0. So 0 the whole structure. Maybe not 0 the whole structure, right? Clear those arrays 0 and 0. That's all we need to do. And that should be what we need. And then everything, oh wait, you've got to reset up the heap again. Yeah, not so bad. So you'd be like core stack clear, address of allocator, blocks and heaps. You would then set this to 0. Then core 0 array. 0 is a C array basically, just as a memset size of that whole thing. Then we need to do the extra code, which will literally just set up the heap again. So it's just this code here. No point putting it in a function. So it's just gonna create a new heap. Wait, we want to keep the heaps around. So you just want to create the blocks again. So you keep the heaps around. You then do a for loop over all the heaps. Allocator heaps count. Something like that. I do have a function for it, but that was easier. And then you need to say heap block start index. See, that's the interesting thing about it. You probably allocate a new block. Yes, you allocate a new block with that heap. It's a free one. Wait, where's the... Does it go on the free list? Why isn't this on the free list? Yeah, you need to put that block on the free list. Yeah, so you go over all the heaps that you've still got and just reset them up with a full-on free heap, you know, one block in the heap. Set the free list head in the right bucket. Yeah. Then start index is whatever the block is, and index perfect. That's what you want. So that's a nice reset function that we can use when we want to, at the beginning of a frame, just clear all that back. Should be nice. Print is interesting, right? This was for debugging. We'll keep this still. We need a heap index. It's kind of got wasted memory, but it doesn't matter. It's not the end of the world because it's got padding at the end. Be not too fussed about it. We'll also need to... Wait, this prints just a block. Pretty lame. Yeah, okay. I guess I used it for debugging while I was dealing with issues. I would like... Right, so here's my validate system, which would ensure that all blocks that bookkeep memory that is physically contiguous. Yeah, so we go over all the, make sure the blocks are physically contiguous. So we had this TikTok bit thing in the allocator. Why was that again? Yeah, to make sure that all of the blocks that have been visited have the same bit that's been toggled, basically. The same, something like that, right? Yeah, then at the end, ensure, okay. So that's why we had it. We'll put it back in there. We'll just chuck a boolean in there. Right, here we go. Validate TikTok bit. So basically every frame that we do the validation, we toggle that TikTok bit thing. And all it's doing is going over every block and toggling that bit that is visited. If we haven't managed to visit a block, we will know because they won't be equal. So we have to go over all of the heaps here. I don't know why this is... Wow. Yeah. I guess I'll just pad it back in. All right. Okay, so we need to go over all the heaps. Allocate a heaps count. So inside the heap, you have a block start index. Then you go over the linked list of blocks. Is free block worthy of free list? Interesting. What a good check. That's something we've got to look at. What is the min? So if a block gets small enough, we'll just be like, it's not worth bookkeeping this because you're never going to bother. Right, we'll look into that. We have gaps in our blocks where the previous start doesn't. Previous start mean. That's kind of a bit of a bad name. It should be called next start. Where's the next start index? So it should be U64. Yeah, I didn't mess up anything else there. That's good. I didn't go the whole way. All right, that's good. So yeah, then it just keeps going over the linked list of blocks in that heap till it reaches the end. Make sure we've reached the next start is equal to the heap, the size of the whole heap. So if not, our blocks do not span the whole allocation of the heap, and there's a problem. One over the heap. GPU VK heap. Allocator heaps data index. Cool. So make sure that the final block ID is equal to the end of the heap as well, because there's a start index and an end index to know physically the final blocks, the start and end blocks. Cool, that's looking good. So next validation thing is visit all the blocks in the unused list. So these are the ones which are not in the free list and not allocated because they're simply too small, or they're too too small. They've got to stay around. I think that's right. How did it go again? Block deallocate. No, these are blocks that we simply... Yeah. Right, these are not that. So when we allocate... So for instance, when we sort of like end up merging blocks, when we deallocate a block and merge blocks, well, you've got these block data structures which are no longer needed, and so we just put them in a linked list, and they're just... Yeah, so we're just accounting for the fact that the blocks end up in this linked list, but they don't reference any memory. And this next bit of validation is, I don't have a comment for it, so it must be extremely obvious what it is. So this next one is going over the block free list. It's going over all the buckets. And then it's just going over all the blocks in the buckets and marking those that have been visited. So I guess it gets the size of the block. So min size and max size in a bucket, since they're powers of 2. So something like this, where we so we go over every block and we're making sure that it is marked as free. Yeah, make sure it's marked as free and make sure it is at least the minimum size and less than the maximum size. And then make sure the linked list of the free list linked list actually matches as well. Yeah, then just carry on in the linked list. Then go over all the blocks and make sure we've actually visited every single block that we are managing right now. And if not, something has gone wrong with the linked lists, how we attach and detach things. Right, so that's the validation side of things. Yeah, so this is pretty handy basically for the test function. I've made a test function which randomly allocates and deallocates stuff. And then it validates it every single time. So yeah, this is how I caught all of the bugs in the BVH allocator. So we're just obviously reusing it for this. So we're just going over n, which I guess is number of iterations. Then we just do 512 random indices, 100 swaps. Yes, we fill in an indices buffer. We swap it 100 times, randomly, go over the indices and pick out a block. If the block, so we just got 1,000 blocks. We say if the block is allocated, we deallocate it. If it's not allocated, we allocate it. So basically we just have to change this to make it make sense, where we do a random number, maybe a little bit higher. Maybe we even go as high as a megabyte or something. Maybe 64 meg, right? Well, yeah, why don't we do the heap min? GPU. Yeah, that min capacity is 228 meg. Random allocation between there. Yeah, we're doing 512 of those. Might be a bit too much. So maybe we'll just do, up to, let's do 32 meg. What's that? That's 16 gig, isn't it? Bit too much still. So we did 8. Yeah, 8 times 512, would that be 4 gig, wouldn't it? Yeah, 4 gig, cool. Nice. Right, so that we're nearly done there. We just got all these utility functions now to do with, that's all the public API. This is the internal API. We did this block one. For some reason, I need a VK result. Local. It's just a macro. Get heap, heap index, block index to a block. Block allocate with a heap. We've done this once, is good. Block deallocate. Right, so we got to patch this a bit. So we'll need to, so we get the block ID. We should not be deallocating the final block in the heap. Yeah, so if you deallocate the final block in the heap, it means there's only one block left. And therefore, we never want to always get rid of... Wait, are we even freeing? Yeah, we are freeing. We're always freeing. So this is actually just throwing the block, by just getting rid of the block. It's not caring about the memory the block is pointing to. It's just actually how do we get rid of this block itself. So if it's a free block, we remove it from the free list. If it's got a block physically next to itself in memory that it's pointing to, we just unlink it. Previous block that it links to, we unlink that. The starting, so this is where we need the heap. So GPVK heap. Heap get. It's stored in the block. And then here we can simply just with the, yeah, so the heap will point to a block, which is the first, which is the block that points to the start of the heap, and it points to the one which points to the end of the heap. And if this block is that, it will basically use the next or previous ID if there is one. Yeah, and there will always be one, since you can never free the final one. Cool. So then the block just gets added to the unused list. It's just a block that exists, but it doesn't point to any memory. So we just zero the whole thing just to, remember the TikTok bit. Tick bit, TikTok bit. Remember the TikTok bit, such that when we do the validation side of things, it doesn't error. And just mark it as being free. And add it to the free list head. Point to the next free item and then overwrite the free list head. Cool, nearly there. So this is unlinking it from the free list. If we have a previous free list block, we get it and make it point to the one that is next to us in the free list. If not, we remove the free list head if it exists. So we find the block. So we get the block size. We find the bucket that it belongs to, since we use power of 2 buckets. If there's no bucket, if the block is so small that it doesn't fit, we don't do this. But then if not, we cycle to the next free list head. That's all this does, is just cycle the next free list head, so it just forgets the one in the head position. Then if there is a next free list block that we link to for this block that we're unlinking, we make the we make it point back to the one before us. Then if there is not one that comes before us, we make this the new free list head. All right, why do we need to do that? Oh, yeah. Yeah, we made this the new free list head. And then we basically just clear these two free list pointers. Cool. Next one. So we've already looked at this. That just cycles the free list head thing. That's correct. We should look out for the word node though, just in case. Right, we're so close. This one sets the next free list head. So it finds the bucket. And block is too small to be added to the free list. Let's forget about it until a neighboring free block is deallocated and joins with it. So that's how we deal with it. So if it doesn't fit in if it doesn't get put into a bucket, it still exists in the contiguous linked list. So the contiguous list of blocks. What's the way of saying it? The contiguous memory that the blocks point to, we link list the blocks that sit next to each other in that. If those don't fit, when we put it into the free list, the block into the free list, if it doesn't fit in any of the buckets, we'll just forget about the block, but it still exists in that contiguous linked list thing. So it means that when we deallocate a free block that it joins with a neighbor, it will join up there. So that's pretty nice. That's cool. What's this thing here? So if the bucket has an item, all right, it's just making the free list head for the bucket point back to this new block, and then we will become the new free list head. Cool. So there's only a few more things we have to do. We've got these sort of magic numbers. It's kind of a bit silly. So what we should do is have a min-max power of 2 bucket thing. And that will be the icing on the cake. So allocator power of 2 min. So I did like 5, right? 5 is like 32, isn't it? Something like that. Let's get a real calculator out. Yeah, 5 is 32. It's way too small. So for resources, you probably bucket-wise, you probably only care about. See, that's like 256 bytes. That's 1K. So the smallest buffer being 1K that we bother, you know, having buckets for, like linked lists and stuff. It just seems like a bit of a waste. Yeah, those ones will just be forgotten about. So should we say 4K? Let's just say 1K. Maybe we'll do 1K. If there's 1KB, if there's less than 1KB, we'll just forget about it. Now the maximum, so this is the biggest before we just start lumping everything into the biggest one, basically. So we could say a megabyte. It's too small, isn't it? 16 meg. This is a lot of buckets, you see. So maybe 1K is too small. But yeah, I'd like to say maybe maybe we'll do 26. So the range is going to be the max, take them in. All right, so perhaps we can make that 16, that'll be 64K. Ought to be good enough, right? 64K minimum power 2, so you'll just waste anything at 64K or less than 64K. I think that'll be all right. So that's 10 buckets. So this magic 12 number. We shall replace this with our new super lovely constant. Oh, I don't really have it anywhere. Okay. Crying out loud. Right. Right. GPU VK mem allocator power of 2 range. Nice. So I won't bother caring about that. Yeah. So this min and max, we've got to be careful. We actually did magic numbers in places. Scary stuff. So we'll look out for 5 and right, 5 and 16. The 5 gets replaced with this minimum. We also had it in that validate function. Yep. Oh, what is this? Okay. Cool. And this 16 one. Nice. So these functions here, they should take in a 64 size. They simply take in that size, do some maths and work out basically which power of 2 bucket we land in, and it gives us back a bucket index, which is, we always take away the min power of 2 because it's just an array of free list head items. Yeah. So this, do we even use the find one anywhere? Yeah, we find, yeah, there's find when we're trying to allocate, and there's insert when we're trying to, right. Cool. All right, that's looking good. So I think we're in a good place there. This one's complaining though. Okay. So we should really look at the word for nodes, or node. Yeah, it's always supposed to have more size than requested. Right, this needs to be a random size, so 64. Cool, so I think that's it. Wait, what's the alignment? Good point. So some random alignment between, we'll do some KB 64K. Maybe we can go all the way up to, yeah, something like that. Be the line. Okay, so I think we're in a good place there for that custom allocator. I'm glad we got that done. So the next thing to do, this was the most complicated part of this temporary allocation stuff. This will allow us to reuse regions of memory and also quickly just allocate memory. When the heaps already exist, it's just a lookup. It's just a lookup into the bucket array, grab the lookup into the array, into this array of free list head entries, and we'll be guaranteed to have a block which is our size, and we can literally just return that after maybe shrinking it. So it's pretty quick stuff. So we should be able to allocate allocate temporary resources, free individual ones back, and then at the end of the frame, clear all of them out. So now it's just a case of hooking up all of the texture and buffer initialization functions, make sure they're all good, and also when we delete the resources at the end, we have to get them to be deferred deleted, basically. So yeah, it's pretty close to being done, but we probably want to make sure we get the texture viewer working as well. So there's maybe 1 or 2 more streams left because I'm unsure about how we get the texture viewer to work, to be honest. But this will be working next stream for sure. But the texture viewer needs probably another stream. So I won't be on Thursday this time around, but Sunday stream will be there as normal, and next week will be normal as well. So yeah, let's find someone to raid quickly. Leave that one open. All right. Okay. I might just bail because I gotta go. But yeah, hope you all have a good, I guess, rest of your week and start your weekend. I'll see you all on Sunday, hopefully. But yeah.